Good morning, everyone. I hope that you had a great weekend and you're doing okay this morning. We're looking today at lesson 30.19, which is the finishing off of the Bohr model of the atom. We already introduced the Bohr model of the atom on Friday, and the main aspect of the Bohr model of the atom is if you know the energy levels that electrons are allowed to be in for an atom, then what you can do is use those energy level differences to predict wavelengths of light that can either be absorbed or emitted. And we learned on Friday that when you have an electron in an atom that falls to a lower energy level, it loses energy. The energy that it loses is exactly equal to the difference between the two energy levels involved. You take the upper energy and subtract the lower energy to get that energy loss. And if it is an energy loss, that means it's explained by the emission of a photon of radiation with an energy exactly equal to that energy loss. On the other hand, if you have an electron in an atom that moves from a lower energy level to a higher energy level, the explanation there is that the electron must have absorbed a photon, and the energy that the photon must have had before it was absorbed has to be exactly equal to the energy the electron in the atom needs to go up one level. So what we're going to do today is look at a couple more examples with the Bohr model of the atom. Then we're going to finish off with this whole section where we talk about models of the atom by talking very briefly about the quantum mechanical model of the atom. And we're not going to get into a lot of detail with the quantum mechanical model of the atom, and I'll explain why that's the case when we get to that section of today's lesson. So we're looking on page 17 of your current lesson handout, and the first example says you have an electron that's in an atom and it falls from an unknown energy state and it emits a photon and it ends up in a lower energy state, and you know the energy of the lower energy state. You're told if the wavelength of the photon is 470 nanometers, what was the energy value of the initial energy level? So we don't know the amount of energy that the electron has when it's in the upper energy level, but we do know the energy value of the lower energy level is negative 12.6 electron volts. And when the electron makes the transition from the upper energy level to the lower energy level, a photon of radiation is emitted, and the wavelength of that photon is 470 nanometers. Well, again, just like we were doing on Friday when we first talked about the Bohr model of the atom, you always want to think in terms of energies. So as soon as I see that wavelength of 470 nanometers, my mind tells me to find the energy of that photon. We can take 1242 electron volt nanometers and divide by 470 nanometers and get 2.6426 eV. Now, how are we going to use this information to find the energy of the upper energy level? Well, the energy of the upper energy level will always be equal to the energy of the lower energy level plus the energy of the photon that was involved. Let me write that down. The energy of the upper energy level will always be equal to the energy of the lower plus the energy of the photon. And you can make a mental note to yourself that that's going to be the case whether the photon was emitted or absorbed. If you take the lower energy value in the atom and add the energy of the photon, you have to get the upper energy because the energies increase in an energy level diagram as you go up. So to answer this question, all we have to do to find the energy of the upper level is take the energy of the lower level, which is negative 12.6 eV, and add the energy of the photon, which was the 2.64 eV. And that's going to give us our answer. So we get negative 9.96 electron volts. And again, I want to point out to you that had this question said, an electron goes from an energy level of negative 12.6 eV up to a higher level by absorbing a photon of 470 nanometer wavelength, the answer to the question would still be found the same way. The upper energy level is called the upper energy level because it's higher. It's higher physically and it's higher mathematically. It has a higher energy value. You always take the lower and add a photon energy to get a higher. All right, an electron in an atom absorbs a photon of a particular wavelength. Why don't we just go ahead and get the energy of that photon out of the way? It's 1242 eV nanometers divided by the wavelength of 655 nanometers. Which gives me 1.896 EV. See, and now I can forget about photons and I can say that it isn't that the atom absorbed a photon, although it did. What my mind is going to say is the atom gained 1.896 EV. Now, in this particular case, we know the upper energy level is negative 5.85 electron volts, and you're asked to find the lower energy level. Okay, so if we were trying to find the upper energy level like example 1, then you take the lower energy level, which we knew in example 1, and add the energy of the photon to get to the upper energy level. It makes sense then that if we're trying to find the lower energy level, like we are in example 2, that you are going to take the upper energy level, and subtract the energy of the photon. And again, what we are doing here has nothing whatsoever to do with whether the photon is absorbed or emitted. We're building this equation based on the energy level we know and the energy level we want to find. If you want to find a lower energy level, you take the upper energy level and subtract the energy of the photon. If you want to find the upper energy level, then you take the lower energy level and add the energy of the photon. So to find a level that's higher, you add the photon energy, and in this case, we're finding an energy that's lower, so you subtract the photon energy. So all we have to do here then is take negative 5.85 electron volts and subtract the energy of the photon, which is 1.896 electron volts, and we will have the energy of the lower energy state. And that's giving me negative 7.74 eV. So E lower is negative 7.75, we will say. And again, just before we move on to the second part of today's video, which is a totally different topic, the idea here is if you want to find a lower energy level, you subtract the photon energy to move downwards. If you want to find an upper energy level, you add the energy of the photon to move upward. And that concludes everything that we're expected to know in this new course structure regarding the Bohr model of the atom. What we're going to do now is look at the quantum mechanical model of the atom. And I told you earlier that we're not going to get into a whole lot of detail in the quantum mechanical model of the atom, and there are a couple of reasons. One of the reasons is that we don't really have that much time. It's a very interesting model of the atom, and we could spend a lot more time if we were sitting together in a classroom having a discussion about the implications of this model of the atom, but we don't have time for that. The other problem, though, is that this model of the atom is really, really difficult mathematically. Every model of the atom we've looked at so far can be described, for the most part, as a physical model. The Dalton model of the atom is like a billiard ball. The Thomson model of the atom is like a ball of chocolate chip cookie dough. The Rutherford model of the atom is like planets in orbit around a star. Even when we get to the Bohr model of the atom, it's not as physical in terms of the representation, but we could describe the electrons in the Bohr model of the atom as being kind of like books on a bookshelf. They can be on the first shelf or the second shelf or the third shelf, but a book can't just be hovering between shelves. It must be on one shelf or the other. It turns out when we get to the quantum mechanical model of the atom, there is nothing physical about this at all. If you asked a physicist who really understood the quantum mechanical model of the atom to describe it to you, they would show you a series of equations. And I'm not even going to show them to you. If we were in class, I would bring them up and that would introduce some discussions about where they come from. The bottom line is this is a highly, highly mathematical model of the atom. So we are looking only qualitatively at this model of the atom. And there's nothing really that you're going to be evaluated on with this model of the atom, but I think it's unfair to just end it at the Bohr model of the atom. So why do we need a new model of the atom? Well, the whole idea of line spectra being related to energy levels within atoms is true for every single atom on the periodic table. But the Bohr model is only able to figure out what the energy levels are for those group 1A elements on the periodic table. I don't know if I'm going to get them all, but hydrogen, sodium, potassium, rubidium, cesium, francium, I have a feeling I've missed one, but all of those elements that are in the very first column, if you like, on the periodic table, have one valence electron, and Bohr is able to calculate energy level values for those atoms. And when you use those energy level values to predict the wavelengths of light that these atoms should emit, we see those wavelengths, so the Bohr model works. But there's a lot more atoms. There's over 100 different types of atoms in our universe. And the Bohr model of the atom is limited to only explaining 6 or 7 of them. The Bohr model of the atom as well cannot explain the relative intensity of the spectral lines. So, for example, if you take a look at hydrogen, the visible line spectrum for hydrogen contains a violet line and it also contains a red line. It contains 2 other lines as well, but there is a red line and there is a violet line. And the fact of the matter is the violet line is very dim. And the reason it's very dim is when you heat up hydrogen gas, electrons do not make that transition that produces the violet light very often. Whereas the electrons make the transition that produce the red light a lot of the time. The violet light is caused by electrons falling from the 6th energy level within hydrogen down to the 2nd energy level within hydrogen. When you completed your assignment from Friday, which was to build that chart showing all of the wavelengths that hydrogen can emit, you would discover that that violet line is from 6 to 2. Whereas the red line ends up being from 3 to 2. The transition from 6 to 2 does not happen very often. And Bohr can't explain that. He just throws his hands up in the air and shrugs his shoulders and says, I don't know why that's the case. So the brighter the line in the spectrum, the more often that transition occurs. And a really good model of the atom ought to be able to explain why certain transitions happen a lot more frequently than other transitions. And a good model of the atom as well should be able to explain any atom, not just atoms with one valence electron. By the way, if you're wondering here, I've got the phrase hydrogen-like atoms. A hydrogen-like atom is an atom that's like hydrogen in that it has one valence electron. In other words, hydrogen-like atoms are all of the atoms in group 1A on the periodic table. So the quantum mechanical model of the atom was developed by a group of physicists, so it's not really named after a physicist. The Dalton model of the atom is named after John Dalton. The Thomson model of the atom is named after J.J. Thomson. Rutherford model of the atom is named after Rutherford. Bohr named after Bohr. The quantum model of the atom is called the quantum mechanical model of the atom. However, Erwin Schrödinger is probably the physicist who is most closely related to the development of it. The quantum mechanical model of the atom is not a visual representation. It's a really highly mathematical representation, as I've already said, that describes the behavior of electrons in atoms. And really, the one thing I suppose that's important for you to know is the quantum mechanical model of the atom talks about probabilities and not certainties. And again, I don't really know that you need to know this in this course, but some of you may end up going on and taking physics in post-secondary where you talk in detail about this model of the atom. The only real way I can explain it to you at this level, without getting into the mathematics, is that when you compare what Bohr says about hydrogen when it's in the n equals 1 state, and what the quantum mechanical model says about hydrogen when it's in the n equals 1 state, is that Bohr says when it's in the n equals 1 state, it is at a certain distance away from the nucleus, we call it the radius, and it happens to be 5.3 times 10 to the negative 11 meters. And Bohr's model is very rigid in terms of where the electron can be found. On the y-axis of these graphs is P of r, and that just means the probability of finding the electron at a particular location. So when the Bohr hydrogen atom is in the n equals 1 state, what does Bohr say about the probability of finding the electron at this value? It's 1, which translates to 100%. In math, we don't like to use percent for probability, but a probability of 1 means 100%. It means that's where the electron is. When you take a look at the quantum mechanical model, it still describes the behavior of the electron in the n equals 1 state for hydrogen, but the probability of it being in this particular location, which is what Bohr says the radius will be, is not 1. It's less than 1. And I have exaggerated this graph greatly, but if we take a look at the probability here, it doesn't matter what the number is, it's a number less than 1. And what that says is the quantum mechanical model predicts, and this is true, that even though the hydrogen atom is in the n equals 1 state, and even though there is an n equals 1 orbit, the electron is not always at that distance. There's some leeway to where the electron can be. There's some flexibility to where the electron can be. And if you do go on to post-secondary, you get into a broader discussion here, because it seems as though as soon as you say, well, the electron can be there, but it can be a little bit closer to the nucleus or a little bit further away, your first reaction to that is, well, what a lousy model of the atom. It's not telling me where the electron is. And you're right, it isn't. But it predicts with 100% accuracy the behavior of large numbers of atoms. And that's basically all we can say about the quantum mechanical model of the atom. If you are interested, you can certainly go online and do some research with the quantum mechanical model of the atom. But what you're going to discover is you will quickly reach a wall that's preventing you from understanding it, and that wall is mathematics. Just to drive this point home, I have a degree in physics, and in order for me to take physics courses where we studied modern physics, which is this model of the atom, I had to be continually taking math courses side by side with all of my physics courses so that when I got to this physics course, I could understand the math. And the math is very difficult. In all of my physics degree, we only applied the theory and the model of quantum mechanics to hydrogen. We never even did it for helium. That's how complicated it is. We spent weeks and weeks looking at the hydrogen atom and the quantum mechanical model in terms of what it says the hydrogen atom is like. Anyway, this model of the atom is able to accurately predict the spectra of any atom. So if you crunch the numbers, and the numbers are difficult to crunch because the mathematics is quite complex, for any atom, you can calculate the different wavelengths of light that those atoms emit. And the predictions you get match the values you measure in a lab. So it's a good model of the atom. It's just really complicated, which is the way of the world. The world is not simple. Anyway, that's it. On the following pages, there are 7 questions, and the 7 questions relate to the first part of this video lesson, which is finding missing energy levels within atoms based on Bohr's model of the atom. I hope that you have a fantastic rest of the day and a good start to the week, and we will talk to you soon.